Welcome, Mindsetters, to another exciting lesson. We're here doing grade 10 maths. Guys, I'm here with Jacques. He hasn't been here. He's pretty much new. So today is his first day, so I'm excited. He's excited. So Jacques, tell us what's happening today.
Ty, today we're going to particularly look at the linear function and more than that, the concept of function at grade 10 level. So I'm looking forward to a very exciting show.
I'm also looking forward to this. So guys, you know the drill. Talk to me on the Facebook page, www.facebook.com/learnextra. And guys, also you can hit me up on Twitter @learnextra. And guys, you know what's up. I still got this calculator that I'm giving away. And I'm also giving away this labeler for the best question today. So guys, make sure you guys keep chatting to me on the page. And I also want to send a quick shout out to Liberty for sponsoring the show. And guys, I cannot stress it enough. Make sure you're making notes, you're writing the stuff down, because it's very important. I know you guys have exams coming up. Always make notes. And guys, chat to me on the page. But for now, we're going to see you after this break. Welcome back, Mindsetters, to this exciting lesson. Guys, I hope you're ready for this. Today we're doing maths with Jacques. So guys, remember, I'm giving away the Casio calculator and this labeler for the best questions. So guys, make sure you get chatting to me on Facebook so I can get those questions to Jacques. If you're lost anywhere, if you need help, guys, this is for you. And Jacques, I think you can take it away.
Great, thank you, Ty.
No problem.
Folks, as we said at the beginning of the show, today we're looking at functions. I'm going to particularly use the linear function to help you understand the idea of what a function is. Now, if you remember last Monday, Dina did this work with you, and she did it quite extensively. So I'm going to revise a few things that Dina spoke about, and today I'm going to talk about the language and the concepts that we use when we talk about a function, and then we're also going to look in detail at two ways of sketching the linear function. Now, what I've got on the screen for you is the notation that we use when we talk about a function. There's one of two ways we write things in your exam paper. We give you an equation of something, y equals 2x plus 1, or we give you the same thing, but instead of talking about this y, folks, we have f of x. Now that is because f of x is the notation that we have preserved to use when we talk about a function. Okay, there's a lot of things that's on the screen here that's very important for you to know and to use. Firstly, I said here, this tells us that whatever we do, we have an input and an output, by the way. So what happens here? We take on a particular value for x, which is over here. So this x value takes on a value. What do we do with it? Well, the rule tells us what to do with it. It tells us to double that value of x, and after we've done that, we add 1 to our answer. Now, that is our input value. So our input is the x, and once we've done something with the x here, we get an answer, and that is what we refer to as the output. But I'm going to talk a bit more about that as we continue through the show. So let's say we particularly want to look at what happens to this function if x takes on the value of 3. So x equals 3. That means we put 3 in the position of x here. We double that 3. That gives us 6. And then if we add 1, we get a y value of 7. Now there's two ways. There's more than one way to talk about that, folks. We can write that as a coordinate pair. So first of all, we can say that is the coordinate pair 3 and 7. Remember, your x values come first, your y values come second. Now there's a reason for that. Let's look at what I did. I chose an x value. That x value was totally arbitrary. I chose it the way I want it to be. I said, let's use 3. After I've chosen my x value, I went to my rule, folks. Now, the rule is 2x plus 1. What is the outcome of that? The outcome of that is I get a y value. Okay, so very important is that what comes out of this operation is my y value. The 3 went in totally by choice. And depending on what goes in, I have something that comes out. The 3 is the input, the 7 is the output. Now in mathematics we call them different things, but it's talking about the same thing. What goes in is what we refer to as the domain of my function. What goes out is got one of two names. Some people call it a codomain, but the language we use in 90%, 95% of the cases is a range. So if you use textbooks to help you study this and you get them online or download them from the internet, sometimes they refer to the word codomain. But what they do really mean here is what we're talking about over there. Okay, so X went in, it was 3, out comes the Y. Now what am I looking at? I'm looking at how am I writing these things. Okay, so in coordinate pair form, the first coordinate in a coordinate pair form is usually your independent variable. I chose X at random. It means, what does it mean? X didn't depend on something other than my choice. Okay, so we say X is our independent variable, and that in a coordinate pair form usually comes first. The independent variable determines the domain of this function. Okay, folks, whatever pops out is dependent on what went in. Hence, I call that the dependent variable. So in coordinate pair form, it is convention to write independent first and the dependent variable second. Another way to write this is to say the function's value in the point 3 was 7. Now that means exactly the same thing. It means that when X became 3, the Y value was 7. The two are related to one another via the rule 2x plus 1. Now when you looked at this rule last time, you saw that it generates odd numbers. Okay, and then as expected, our output value was indeed an odd number. So if I want to talk about this, I can say that I've determined f of 3. Okay, and f of 3, as we saw, was then equal to 7. This means if x is 3, the y value is 7. Okay, so folks, important, the language we use. Functions have input values. Those are the values that are usually the x value, and I say usually the x value because in science you guys also work with graphs where you work with a horizontal axis when you sketch these and you work with a vertical axis. So if I talk science and I talk a time distance graph, the time is the independent variable, hence it's on the horizontal axis. The distance then will be on the vertical axis because the distance I traveled depends on the time it took me to travel that journey at a particular speed. But that's for the scientists, that's not for me. What I'm trying to show you here is that whatever is independent in the function domain, when we talk about any functions, goes onto our horizontal axis, are the numbers that are first in the coordinate pair form. And the dependent variables are then the outputs, or the stuff that goes vertical. Okay, folks, so that's the language that we're going to use, and very, 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 very important is the idea when I talk about a domain and a range of a function. Okay, so as we said here, we show you again, the output of a function, in other words, the f of 3 or the 7, is completely dependent on the input. There's a dependence there, and that is what functions are all about. Okay, I put something into a function machine. What comes out is called an output. That output totally depends on what it is that I put into my rule. Okay, now some people call that rule a formula. I like to call it a rule, else every time the rule changes, I'm creating new formulas. Okay, now folks, remember here, write this down if you don't have it somewhere. Remember that the set of input values that apply to a certain rule is called the domain. So the domain and the input values is one and the same thing. Okay, we're going to talk about notation later on. How do I write the domain and how do I write the range when my teacher asks me that in a test? I'll show you, we'll talk more about that just now. Then also the corresponding output values. The corresponding output values is what we refer to when we talk about the range of these functions. Now there's a new word here, the word corresponding. Folks, every input value corresponds to an output value in the notion of a function. Some teachers, when they teach functions, let me do this on the side here, I hope you guys can see it, use the idea of a black box. And we say something goes in. Now, in the case of this problem that we're looking at, our rule in this black box is 2x plus 1. So in comes the x values, or the domain for this rule. And then out is what is my output values, which is my y values, if I talk about it as a purely mathematical relationship. Okay, folks, so there's some very, very important things here that you have to realize and that you have to make your own. And that is the language that I use when I talk about these things. If I talk about input values, I'm talking about values that come first when I refer to this in coordinate pair form. I talk about the values that are the independent values in my function itself, and the fancy mathematical name for that would be the domain. Okay? If I talk about output values, I'm talking about the values that came to be after the x went through the black box and delivered some particular y values. Okay, those y values is what I either call a codomain, or then the very popular word that we use for that in the classroom is indeed the range. Okay, then lastly what I've got for you here is in some cases these two sets could be limited or restricted. Now it depends on the type of function that you look at. If I just look in general, we're not going to look at this function today, but if I have an x and a y coordinate, let me just extend my page a bit. If I have an x and a y coordinate system, and I have a straight line, there's my dependent variables, there's my independent, and I have a line, and I indicate with arrows on the side of each line. Folks, that means this line continues indefinitely. So if I move on and move on and move on and I move into the studio next door to this one, there will still be some y value that corresponds to the particular x values that I'm looking at. If I have a different type of function, which you're going to learn about when you go to university, I'm just going to draw any one. It starts there and it goes that way. Can you see, folks, at some point there, this graph started. So if I go to this side of that point, there is no domain. The domain doesn't have x for this particular function, does not have x values. Let me just move this back where it belongs. There we go. And let's say that that's the point where x is minus 2. So if I move to minus 3 for that particular function over there, that minus 3 is not in the domain of the function because the graph started there. Now that's what I mean when I say sometimes the function itself restricts the domain. Other times your teacher might ask you, sketch this line for me, but only from minus 2, x equal to minus 2, up to x equal to 7. Then you work with a very limited domain. And then your domain will run from minus 2 right up to 7. And then you'll find whatever your corresponding y values would be for that domain, you'll find by plugging those values into the equation. Ty, what did you think of that? Do you find this type of thing difficult when you were at school? Did you find it difficult to understand?
Well, when it was explained to me this clearly, No, I actually found it pretty easy. So guys, I hope this is as good for you as it was for me. So I'm having fun. It's making sense to me. So I think we'll go to an ad break quick. Give these guys a little bit of a break. Let them catch up a bit. Make sure you guys get a snack, get some water, get ready for the next session. You guys know the drill. Make sure you keep chatting to me on the page. I'm seeing a couple of people. Hi, Kashifa. I see you. The usuals. So guys, make sure you come back after this break. Welcome back, Mindsetters, to grade 10 math. I hope this has been fun for you guys. And before I get my head chewed off, Noxie, hi to you too. I see you. And guys, yeah, just keep chatting to me on the page. And I see you, Mo. What's up? And guys, just keep chatting on the page. Let me know what you're thinking. If you're lost anywhere, if you need help, make sure you get those questions to me so I can get them to Jacques. And I think, Jacques, you good to go?
Excellent. Great. Thank you, Ty. Thanks, folks, for making contact with us. What I'm going to talk to now is particularly the linear function. I'm going to talk to the mother of all the linear functions, and that's the line y equals x. Y equals x is sometimes we call it, in certain textbooks, certain areas, they call it the identity function. It is the linear function's mother function. Now, people talk about this mother function as the parent graph. So from now onwards, I will use the word parent graph because that's most probably what your teacher also uses at school. Folks, what happens in that function? If we interpret it y equals x, we put an input value in of 2. Can you see that the output value of x is 2, the y value will also be 2. So the input and the output values are identical. It's the same thing. Hence the word, the identity function. Folks, now very important. Later on, when you're going to look at transformations, this line is going to become very important. Okay, we're not going to look at the transformation idea. We're going to look at the properties of the linear function. Okay, so first of all, we can write it as y equals x, or in the same notation, we can say f of x is equal to x. Remember, it means exactly the same thing. Sometimes you'll find books saying y is equal to f of x is equal to x. Okay, remember this f of x notation is only reserved for a function. If we plot the graph, then surely what we can expect is something that looks like that, where your domain is on the horizontal axis, your range is on the vertical axis. Let me just get that down a bit so you can see the y value up there, the y. And then for every x, if x is 1, the y value is 1. Hence, the point that lies on this function is the point 1, 1 in coordinate pair form. If x is 2, the y value will be 2, and hence the point 2, 2 is on this function. And so a lot of other points are on this function. But we're talking about a very basic straight line function. We're talking about the parent graph for all the linear functions. Okay, now what I want to look at next is the way we represent this linear function in textbooks. There's two ways to talk about it, depending on what you're doing. The first thing would be to write it in what we refer to as standard form, and your standard form is y is equal to mx plus c. Now, these forms have different uses, folks. If I want to write it as mx plus c, which is the first form, I can see there's a parameter in front of the x, which is m, and then there's a c that's not connected to the x itself. So what would that mean? That has various meanings in what we're going to look at when we talk about the function. First of all, the thing that is in front of the x is usually a number. That number can range, can be 0, can be any other number. It can be negative, it can be positive. Now, last week, I beg your pardon, last week you saw what happened to this function as the value of m increase or as a decrease. Okay, you also saw what happened to it most probably when it was 0. If you couldn't watch last week, don't worry, I'm going to go through that with you again today. Then we have what we call the general form. Now, the general form for the linear function is ax plus by plus c is equal to 0. Now, usually your teacher will tell you in a test, if you use the function, you're drawing the line, or you're busy working with a line, or you're finding the equation of this line, your teacher will tell you, leave it in the form y equals mx plus c, or in the form f of x is equal to mx or equal to something, or the form ax plus by plus c. The most popular one, however, is the standard form. Okay, folks, now between the standard form and the general form, there's nothing different. It's just the way we're writing it. I'm going to focus on the standard form a bit. If I look at mx plus c, and I want to look at the function and the way that value of m will influence the way the function would behave. I'm not going to draw it. I'm looking at the behavior. Then I think the best way to see that is through a table. We are looking at input values. X, now I particularly used a few here. I used -3, -2, 1, 0, 1, 2, 3. Doesn't mean that I'm not going to use anything between -2 and -3. Okay, I'm just using those particular points to make a point. If I plug it into the function y equals 2x, there it goes. 2 times -3 is -6. Then I go to the next point where x is -2. I get 2 times -2, it's -4. Then I go to -1, 2 times -1 is -2. And so forth in that function. Now what's important to notice here is look at the way this growth is happening between those outputs. Remember, I'm working and focusing on the output for a particular input value. And I'm going to write this down. This here is the domain, and that there will generate the range of my function. Okay, so here's the domain values, there's the range values. Interesting to see here, y equals 2x. These output values differ by 2, when my x's differ by 1. So as my function is running through its domain from the very negative numbers to the positive numbers, what is happening to the y values? They're differing by 2. In the identity function, if you can recall the identity function, they differed by 1, because the coordinate pairs were 1, 1, 2, 2, 3, 3. Okay, so your y values went from 1 to 2 to 3. They differed by 1. Here, it's differing by 2. Let's go and have a look. On the other side, if I use still the same input values, but I now look at a different function. Instead of looking at y equals 2x, I look at y is equal to 3 of x. So, you'll notice what is changing. Let's talk about that in the table. The 3 that's in front of the x are these 3's that are in front of those brackets. My input values goes into the bracket, and I generate a whole set of output values. Now look at the poetry over here, folks. Now all of a sudden, my output values are differing by 3. When I was working with 2x, they differed by 2. Now they're differing by 3. So what would I expect with 4x? That they would differ by 4. Well done. You can see the increase there is 4 between the output values. Now please notice that your x values, in other words, your domain is still increasing at a rate of 1. So I'm going from 1 to 2, from 2 to 3, 3 to 4, 4 to 5. The y values are increasing at a larger rate, the bigger the number in front of x. It determines the rate at which the y values, the output values, are growing. Okay, hence you would have heard your teacher say this, the word gradient. And the word gradient is the same as the rate at which something is changing. Okay, let's look at 5. And I can hear you say at home, at 5 it differs by 5. Look at that. exactly what we expected. Now, folks, if I were to draw this, if x is 3, look at this, x is 3. On that function, the y value is 6. On the second function, the y value is minus. Now, I think let me go to the positive numbers, not the minus 3. Let's just go to a small number like 1. If x is 1, the y value is 2. If x is 1 on this function, the y value is 3. If x is 1 on this function, the y value is 4, and then it is 5. So if you look at my arm, if that was the line y equals x, then 2x would run steeper. 3x would run even more steeper. 4x will be more steeper. So the bigger the number that I have in front of the x over here, the bigger this number is, the steeper the line will increase at. The y values increase at a larger rate. Okay, folks, and that is what we call the gradient of my function. It has another name, it has a slope, and some people refer to it as a rate of change. The rate at which the y values are changing as the x values are changing. Now we talk about this, folks, by looking at values. This is convention. You can talk about it any way you want to. But if I use the word convention, it means this is how everybody in the world is doing it, so that we all understand what we are talking about. Okay, so if I say to you, as x is increasing, y is increasing, then I'm talking about a function that increases. So if I want to talk about a function that decreases, I'm not changing the way I look at the x's. The x's, I still look at it in the same way. And then the y values will be decreasing. Okay, so what I'm trying to say is, if you want to talk about a function, something needs to stay the same to look at something that is changing. Now in this case, particularly, I kept the c the same, and I look at what is happening as my m values are undergoing certain changes. Let's see what is the effect. Let's first write that down as our conclusion here. What happens as the value of m on the straight line is changing? That is the number that is in front of the x. It is the gradient. Okay? So first of all, this is my gradient. We wrote it down just now. As m increases, so as m is increasing, the graph becomes steeper. Now you saw that when Dina spoke to you last time about the straight line. So this is a small value of m. If you look at my arm, that's the slope. There's my line. Okay, that slope is, let's call it 1. If I want to draw a slope of 2, I have to increase my y values. Now if you think about this logically, folks, I want you so badly to understand this, because this links beautifully with what you're going to learn one day when you do transformation geometry. This 2 in front of the x here, if you want to talk about it as a transformation of the function, it means it is doubling the y values. This one is tripling the y values. This is making the y values 4 times as big for the same x value. Okay, so the bigger that number becomes, the steeper the graph rises. Now, I'm only talking about positive ones now. If I had a negative gradient, remember, you saw, if you look at my arm here, that is how your line would slope if you have a negative gradient. So if this is a gradient of -5, the number is becoming bigger if I go to -4. Don't make the mistake to think that -4 is smaller than -5. It's bigger than. Okay, that's one big thing you must remember. So if that's -5, you saw that this will be a gradient of -4, -3, -2, -1, and so forth. So if from the negative side the x becomes bigger, the line becomes flatter. And if I work with positive m values, the bigger they come, it goes steeper. Okay, let me just see what we're going to focus on next. We're going to focus on the change of C in our next focus. Yeah, we're still busy with linear functions. Ty, have you got anything for me?
Well, it's still a bit quiet on the page. I'm telling the guys to keep chatting. But so far, I only have one. And I know it's kind of a little question, but as we always tell the guys, there's nothing like a silly question. As long as you have questions, that's what matters. Sibongile wanted to find out what's the difference between substitution and elimination. If you could just help her out quick.
Okay. Sibongile, that's a very good question. Substitution is what we did here when we did f of 3. Okay, if I say f of x is equal to 2x, f of 3 means take the x there and substitute it with a 3. It means to put something in the place of something else. Okay, now I know why you're asking that, because you're learning your simultaneous equation stuff, where your teacher uses the language and says, well, get the y by itself and substitute that into the other equation. Okay, so substitution mathematically means take something, put it in place of something else in another equation, particularly maybe in this case. Elimination means to get rid of it. So if I subtract two things from each other, if I subtract 5x from 5x, the answer is 0x. There's no more x. So what I've effectively done is I've eliminated the value of x. It's no longer there. So I hope that helped you.
Yeah, and I think for now, I think that's about it.
Okay.
Still waiting for them to come in with a couple or more. But you good for an ad break?
I think that's a fantastic idea.
All right. So guys, you know the drill. Go grab something to snack on, get some water, get some juice, make sure you're glued in front of your screen after this because we're having another session. And guys, make sure, just keep chatting to me on the page so I can get those questions to Jacques. So guys, we'll see you after this break. Welcome back, Mindsetters. Guys, I hope you're having fun, and I hope you're paying attention. You got your notes and your pens and your pads out. Because, guys, up next, this session is going to be actually getting a little bit faster. It's going to be more intense because we've got a lot to cover. And, guys, I'm still giving away this calculator and the labeler for the best questions on the page. So, guys, make sure you post. All right, Jacques, get straight into it.
Excellent, Ty. Let me summarize, folks. I saw now that you're asking a lot of questions on gradient, so let me quickly summarize that. If I talk about the gradient of the function, we established it is the m in my function. It's whatever in the standard form is in front of the x, folks. Now, if that m value is a positive number, we have a possibility for the line that would slope this way. It will, in fact, definitely slope that way. Then if that m was a negative number, it would slope the other way. Okay, but there's now very important things that could also happen to this gradient, folks. Now, why do you think I cannot walk up that wall there? And that is based mathematically, one of the explanations could be the idea of the gradient. Okay, we're going to go into detail in that gradient now. If my gradient is 0, my line would be a horizontal line. And there's a reason for that. Our gradient is a change in our y value over the change in the x value. Now, folks, that delta, that little triangle, we call it delta. Mathematically, it means the change in. So there's two y values that you need to find the change between them, and they are based on the two x values. Okay, that gives us the gradient. What determines that this gradient is 0 is based on the idea of a fraction. If the top part of the fraction is 0, the gradient becomes 0. So then I will have this idea for my line. My line is horizontal. If the top part of that fraction has become 0. Okay, because 0 divided by anything other than 0 is 0. So the result is a horizontal line. Okay, there are cases where this delta x is going to be a problematic, and that is where the delta x is naught. Very, very important, and we'll talk about that just now. What happens because it's a fraction if the denominator of that fraction becomes naught, and how does it then affect what I think of my line? Okay, so if that outcome there is positive, the line is increasing. Let's use the right language. And if that very same gradient is negative, the line would be a decreasing function. That means as the x values increase here, the y values are increasing, but over here, as the x values are increasing, the y values are decreasing. It's becoming smaller and smaller. Now, I quickly want to look at the effect of the c on the line. Now, remember where the c comes from? We're looking at mx plus c, the standard form of the line. Now, I did the same as what I did for the gradient, folks. I worked the mother function, the identity function. You'll see input, output exactly the same. Now, if I go to x plus 1, what happens? The input, the output has increased by 1. If I go to x plus 2, the output of the mother curve has increased by 2. Now, there's your mother curve. Y is equal to x. What happens if I add 3? From the mother curve or the parent function y equals x, the output values increase by 3. But now what's important here and very interesting, can you see, folks, these output values, the difference between them is 1. The difference between these output values are also 1. Look at that. The difference between the output values are 1. Difference between the output values are 1. Difference between the output values are 1. So what does C do to the mother curve? All it does, if you think about it as an algebraic event, all that this value of C does is after we have doubled it or multiplied it with a value of m, we just add that number to the output value. We add 1 to the output value after the input has gone in. Okay, so on the graph it would mean this graph, if this is y equals x, and I add 1 to all the y values, use your common sense now. Don't always just think for mathematics I have to do thousands of formulas to try and understand it. If my arm is y equals x, and I add 1 to every y value, folks, then this graph is just going to move up 1. If I go back to y equals x, and I subtract 2, what's going to happen? The graph is going to drop by 2. Okay, so all that C does is it either lifts or drops the graph. If that C value is positive, it means something particular. Now, I want to go back to my very first slide that I used today, and that's the one where I had the parent graph drawn onto the slide. Here we go. That's y equals x, folks, the one that you see on the screen. So if I want to draw in y is equal to x plus 1, it means for all these y values, I need to add 1. So the new point on my graph, if I use another color, let me get the blue, the new point on my graph for this point would be the point 1 and 2. Why? Because this told me add 1 to the y values. So the point that will be on the graph is the point 1 and 2. Now the same for 2 and 2. 2 and 2 would mean I take this y value of 2 and I add 1 to it. I get 2 and 3. So all that is happening here, 0 and 1, because it was the point 0, 0. My graph, if I quickly draw that in, would just have lifted up by 1 unit. So if that C value is a positive, it means it lies on the positive side of the mother function. It lies above it. Now, what's very nice here as well is this C value corresponds with the y-intercept, folks. Now, important. It's very easy if somebody tells you the constant is always the y-intercept. Why is it so? The answer to that is, if I look at the y-axis and I make x equal to 0, then I'm on the y-axis and I'm finding the y-intercept. So for all these lines, if I look at y is equal to 2x plus 4, if I make x 0, what stays behind is the 4. And that would be the y-intercept of that particular line. Okay, we said we're going to pace it up a little bit. I wanted to particularly focus on the gradient. Okay, the gradient have different names. M is the symbol we use for it in standard form. We call it a gradient. We can also then give it another name, a slope, or it's sometimes, as I said, referred to the rate of change, as the rate of change. Okay, there's my 3 cases that I work with, but you would remember I said, hang on, this is a fraction. Delta x can possibly, by mistake, become a 0. Now, those things have names in maths, folks. If I have a fraction of 0 over 0, we call it an indeterminate in mathematics. So your teacher might someday use that word. If you want to impress them tomorrow, talk about that when you draw the line. Okay, if you have something divided by 0, there's something funny that's going to happen. Okay, now if you look at the nature of this graph, this is negative. The more negative this gradient would be, folks, the line would lift up. So the smaller the values of y, of m. The bigger the values of m, this line would come, it will go through 0 there to move into positive gradients. What happens, and this is very interesting to think about, what is going to happen if my gradient, which is the change in y over the change in x, if this delta y can take on any value except for 0, but my delta x becomes 0. Now that's based on this whole idea of a fraction, folks. The smaller the denominator of a fraction, look at this. I can have 5 divided by 4. That's 1 1/4. If I have 5 divided by 2, that is 2 1/2. 1 1/4, 2 1/2, it's becoming bigger. If I have 5 divided by 1, it's bigger, it's 5. So we've gone from 1 1/4 to 2 1/2 to 5. Now I can say 5 divided by 0,01, and that answer would be 500. Now imagine that number becoming smaller and smaller and smaller and smaller and smaller. Can you see what's happening to the outcome? It's becoming steeper and steeper and steeper and steeper. And that's my explanation for why I cannot climb or walk right up to that line, because the gradient is too big for me to overcome. If a line is vertical, if a line is a vertical line, that's the typical example of a line where the gradient had a problem. In other words, there was no change in x. Now, folks, put this on the Cartesian plane. There's x, here's y. This is the line x equals 2. Now, that means what? It means there's a coordinate pair 2 and 4. There's a coordinate pair 2 and 3, 2 and 1. All the x's are the same, 2 and 4, 2 and 3, 2 and 1. So there is no change in x. The change in x is 0. Hence, the line is a vertical line. Okay, that's the first important thing I wanted to talk to you about. The second important thing that you will always need to find are the intercepts with the axes. Now, on my vertical axis, that's the y value. The x values are always 0. Okay? Hence, it has an equation. It's the equation x equals 0. So for the y-axis, all my x's are 0. So if I want to find a y-intercept, in other words, where the curve cuts it, I need to make x naught. But that's beauty. That is absolute poetry. If you think about what will then be the equation of the y-axis, well, the equation of the y-axis is the line x equals 0. It's a vertical line. Now, the same happens with the x-axis. On the x-axis, all my y values are naught. So if I want to find out where a line cuts the x-axis, I need to make y naught. Important grade 10s, don't forget. That will also be the equation of my x-axis. Okay, so those are two very important things that we will now apply. If I look at, I need to just quickly get rid of that thing. There we go. Methods of sketching the straight line graphs. And I want to end the show with this tonight. The quickest way for you to use, to sketch the straight line graph is to use what we call the dual intercept method. That means find the x-intercept, find the y-intercept, and connect the two, and there's your line. Well, let's have a look. The equation I want to look at is, the equation is y is equal to, let me make space here. Let me just get this down. There we go. Y is equal to, and take a pen, y is equal to 2 over 3x, and I'm just going to use the one that I've got here on paper, plus 2. Okay, folks, there's two ways to do this. The quickest one, as I said, will be the dual intercept method. Now, please, it means something important. Dual in maths means two. A straight line has two intercepts. It has an x-intercept and a y-intercept. And if we found it, we found the line. So let's first find the x-intercept. For the x-intercept, remember what did we say? Make y equal to naught. Now here, if y is naught, I have 2 over 3x plus 2, which is 0. I multiply the whole thing by 3. I get 2x plus 6 is equal to naught. I kick the 6 over. 2x is equal to negative 6. Don't forget, if you transpose over the equal sign, the sign changes. I divide by 2, and x will be minus 3. Now I've got my x-intercept. My y-intercept, all I need to do is make x naught. Now, folks, look at my hand. Look at my hand. If x is naught, this part disappears. So I'm left with y equals 2. If x is naught, the y value is 2. And all I need to do, there's my Cartesian plane, my x-axis, my y-axis, there's my origin. My x-intercept is negative 3. So off I go. There's my minus 3. My y-intercept is 2. Plot it. And then draw your line. Start from that side. Through your y-intercept, through the x-intercept. Now you can see my line's a little bit too high, so I'm going to move it into the intercepts. Okay, folks, that's your dual intercept method. Very important. Find the x-intercept, find the y-intercept, and you can sketch this line. That's one of your two methods. Now, unfortunately, I've spent so much time talking to you about the gradient. It is the most important part. The concept of the linear function is that gradient. I didn't have time to talk about the second method of sketching these lines. But Ty, you know what? There's always another day that we can look at that.
Yes. Well, I don't know if you want to just do a little quick recap of that, of what you covered today, make sure that they really get it, because I think, we've got a little bit more time.
Sure. Yeah. Sure, let's do that, folks. Remember what I said today. The language we use when we talk about a function. Input values are in the first position in coordinate pair. We have another name for that. That is the domain. Why? Because it's independent. The output values depend on the input values, so those are the range of my function. Okay, so you have domain, you have range. You have a relationship there. The independent variable determines what happens to the output value. Okay, so that's independence, dependence. Independent on the horizontal axis you saw there, My independent variables are always horizontal. My dependent ones are the ones that are vertical. Then you also saw us talk about the gradient, the different values of the gradient and how that changes the slope of the line. And then lastly, very important, how to sketch the line. Quickest way, the dual intercept method. Practice, 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 folks. You'll get full marks for this.
Exactly, guys. So I hope that helped you out, and I hope you guys are paying attention. So guys, this is where we're going to say bye to you and see you next week. In fact, no, see you tomorrow for you guys. Anyway, this is me signing out. Ty, peace.